Yeah, yes, it's the cost to go both ways with the fire going on.
Oh, we're getting sentimental today.
Yes, we are. And I don't need in your hair any more of your sediment.
Yes, sir.
See? Anybody else want to try sediment, Joe?
No, it didn't, the last one didn't lay over well.
Oh.
I don't know, that might be too low for me.
It'll get all silty up in there. Okay, so what is sediment, first of all? It's just any sort of particles that are found in aquatic systems. Nothing too exciting about that. And it depends on what's happening to it. So this is a picture here. You can see this is Cane Creek, where we did some work. Only at this point in Cane Creek, the water would have been, if you were back in Cane Creek doing this, the water would have been 3 or 4 feet over your head. At this point, this is when it's kind of flashing. And you can see the water looks turbid. And it looks turbid because that's a suspended sediment. So that's one type of sediment. When it's moving, it's suspended, and when it's on the bottom, it's deposited. And it fluxes in between both of those forms, depending on what's going on. It can be organic or inorganic. We tend to think of inorganic sediment a lot, but it can be both. So, again, we refer to the inorganic. The organic is important there, and if you're making measurements of sediment, total suspended sediment, you have to define it. Is it organic or inorganic? If you say that this much sediment, some people report it as total sediment, total suspended solid. Some people just report it as sediment. You don't know. Next question is, okay, so it's particles. So again, mostly inorganic. So I want to talk about these particles have different sizes. So, and I use what is called the Wentworth scale for measuring. There are different scales that are using this. And the Wentworth scale, from the largest to the smallest, is boulders are the biggest particle size. Okay, so that's everything that's greater than 256 millimeters on what is called the beta owl angle. So if you were measuring this rock here, would you measure it this way, or thickness?
Thickness?
No. You measure, this is called the beta angle. This is the alpha, beta, and the gamma is the thickness. So it's this angle here we would be using on all those rocks. That's the standard format on measuring rocks. 256 millimeters. Show me 256 millimeters.
That size of your fist?
About the size of an inch.
Nope. .6 millimeters, about the size of an inch.
So
That's a quarter of a meter.
Mm-hmm.
Okay, try to remember your size. So it's a big thing. Okay. Cobble then is the next size down, and that's basically 64 centimeters. Okay, so about yay big. 256 is what we call cobble. So all these terms have real meaning. So basically, what you're looking at here. So there, I don't see any cobble in this picture here. Pebble, I see. This would be pebble over on this side. 16 to 64 millimeters. Gravel, this would be gravel over here. 2 to 16 millimeters is gravel. Next smallest is sand. And then sand is basically, so 2 millimeters is the same thing as 2,000 microns. So since we're talking small, we shifted the scale here. So 63 to 2,000 microns, or 63 microns to 2 millimeters, same thing. That's sand. Then any smaller than 63, but no smaller than 4 microns is what we call silt. And anything clay is basically then 1 micron to 4 microns in size here. Okay. There are more useful descriptors to use for this. Okay, so when I'm in the field, I don't sit around and measure every rock. Okay. What I do is boulder. I don't want to pick it up. That's real easy, real quick. Okay. Cobble. pick it up and you look at that rock and you say, will that fit in my mouth? If it will, if it won't fit in your mouth, it's not common. So, I mean, if it won't fit in your mouth, it is common. Pebbles, then basically pebble, that's about the size of a good old skipping rock. Gravel, stuff you see at the bottom of a fish tank, gravel size. Sand just feels gritty. Silt, it'd be about the size of ground flour, cooking flour, wheat flour. And clay feels greasy, so it's kind of small when you feel it. So these are basically, instead of having to measure everything, this is generally how a field biologist would sort of look at these kind of things. So that's the inorganic sediment particle size. Organic sediment also has particle sizes. They're slightly different. Okay, so what we refer to in organic sediment, the proper name for organic sediment is particulate organic matter. Organic matter particles. There's 3 classes of particulate organic matter. We don't use the Wentworth scale for these. Okay. 3 general sizes. First, coarse particulate organic matter, often referred to as CPOM. Okay. And basically, this is anything bigger than a millimeter, which is, if you think about that, that's a huge size range. So it could take a little piece of a leaf, and that would be coarse particulate organic matter. I could take the entire tree floating down the river. That's coarse particulate organic matter. So this is a massive size difference here, coarse particulate organic matter. In terms of biological function, though, it's all about the same. So that's why they're together. So the next layer down from coarse particulate organic matter is fine particulate organic matter. And fine particulate organic matter is basically anything smaller than 1 millimeter, but larger than, here's a strange value, greater than 0.45 microns. There's a reason why they pick 4 or 5 microns. Okay. Anything smaller than 0.45 microns is called dissolved. Okay. Now, dissolved means something to us. It means that the bonds have been broken, things or other bonds have formed, and it causes something to actually dissolve. Well, this term, basically, things may truly be, you may have dissolved carbon. A good example of dissolved carbon might be like tea is a good example of truly dissolved carbon. But if you had little tiny pieces of tea floating around that were smaller than 0.45 microns, it would really be particulate, but we call them dissolved at that point. They are so small, we call everything dissolved. Why, in God's name, did they pick 0.45 microns? That becomes a big question. And the reason is, to separate these 2 groups, you have to filter them. And this is a pretty involved process, takes a lot of filtration. It's also an expensive process depending on what sort of filters you use. So this is basically, if I want to figure out how much, I have this water sample, and I want to figure out how much particulate organic matter, how much material over 0.5 microns is it, I'd pour a no volume of water into this vacuum filtration apparatus. The filter is right here. The filter would catch everything less than 0.45 microns. Everything else would come through. Okay. And the reason why 0.45 microns, because this is basically what happens, the water is brought down onto these glass fiber filters. The smallest size that you can mass produce and still be financially cognizant, not cost you gazillions of dollars, is a small, that can still be reasonable, affordable. It's 0.45. So you can buy a whole lot of 0.45 micron filters. So that's, the cutoff is simply because of economics. That's why anything smaller than that. Yes, I could filter down to 1,000th of a micron, but that filter would probably cost several $100s. These filters here probably cost about $1 each at most. So that's why the reason for, it's simply a monetary reason. All right, so as I said, they're sediment fluxes between suspended and deposit. It is suspended and it is deposited. Okay, so if I move from suspended sediment to deposited sediment, in other words, and again, we talked about all the properties of water, viscosity due to temperature, viscosity due to velocity, all these things affect the ability to carry sediment. So when sediment falls out, we call it deposition or siltation, which is a very bad term. Okay. Why would siltation be a bad term? What does it sound like happening?
Having a lot of silt in the water.
It sounds like silt is falling out. Well, what if it's sand falling out? It's still siltation. What if clay is falling out? It's still siltation. Okay, so basically we tend to use the term deposition, but siltation is used by very common, people talk about things like silt fences, stop erosion. Well, that stops more than silt, it stops all sorts of stuff. When you move from deposition to suspended, basically that's suspension, resuspension, erosion, elutriation is used a lot in scouring. The term elutriation, basically, so where sometimes they're in the world, there is sediment in various places, like behind dams and all that. They got there many, many years ago. Like if you go behind a dam, as we all know, the lakes slowly fill in, they silt in, they have life. They're born, they have a life, and then they die. The dying is due to the silting in. Well, the silt comes in over a long period of time. And in many dams, there's silt from back in the 50s and the 60s. And if you start to clear water out of that, if that water starts to elutriate that material, you're suddenly reliving the 50s and the 60s. So organochlorines, DDT, all sorts of stuff comes back up. So this term elutriation talks about, it basically deals with resuspending of sediments, resuspending of old sediments. And all these things mean the idea of moving from deposited sediments into suspended sediments. Okay, what factors influence the flux? This is all review. Particle size. Yes. Clay particles tend to stay in suspension a lot longer than cobble. Changes in water velocity, we talked about that, then it changes viscosity. As I increase water velocity, I increase viscosity, and I can carry more sediment. And the opposite is true too. And water temperature. Basically, as I chill water down to freezing, the density pretty much increases until I hit about 4 degrees C, where it's the most, and then because it's dense, it can hold a lot of material. All right, where does sediment come from? Okay, all sorts of places. Before I get to that, okay. Here are two important limnological terms. I can't remember if Greenwood or I gave you these terms before. First term is autochthonous. Have we used this term before?
Yes.
Green was talking about algae, so since algae do photosynthesis, they would be an autochthonous form of energy to a lake that they live in. So because they are within the system. So autochthonous means from within the system. So if I am sustaining myself on food that I grow in a garden in my house, that is an autochthonous food source. I'm growing it myself. It's within my neighborhood, my system being marked. The other term is the resource originates from inside the habitat or inside the ecosystem, depending on what we're talking about. The other term then, so this is again the example I did. So algal photosynthesis is an autochthonous source of energy to the lake. The energy was grabbed by the algae, the little bugs ate the algae, everything happened within the system. So the opposite of this is allochthonous. Allochthonous from outside the system. So if I'm eating vegetables in my garden, that's fine and dandy. That's an autochthonous source. If I go to Walmart and buy my vegetables, That's an allochthonous source, because those vegetables were grown somewhere else in the world and brought to Walmart, brought into this ecosystem of Martin, Tennessee, and that's outside the system. So the resource came from another habitat or ecosystem. Example for that, again, with the lake example, algae is not the only source of energy, organic energy to a lake. Another source would be basically, and you can see it this time of year all the time, leaves from the terrestrial area come floating down, land in the lake, sink, and they become the basis of a detrital food web. So that's a allochthonous energy source. Okay. So it's an awful lot just to teach you these two terms, autochthonous and allochthonous. We can apply these terms to sedimentation. Okay. So autochthonous sedimentation, okay, that's basically resuspension within the system. So I've got a stream that's moving very fast, carrying a lot of sediment. It slows down because of changes in discharge. That sediment falls out. When the stream comes back up again, its sediment in the stream gets resuspended. So that's an allochthonous source. Okay, so changes in current velocity. Sometimes it'll suspend, sometimes it'll deposit. You see that all the time. Okay. Another thing is resuspension by wind action. So in shallow water habitats, we talked a little bit about fetch, where the wind comes blowing against the shore, causes things at the bottom to stir up, and it gets resuspension that way by wind action. Okay. Bank erosion, same sort of thing. It's basically non-vegetated banks are susceptible to wave action. The silt and sediment are already in the system, they're just being resuspended. Allochthonous sources then, overland flow or stream flow. I talked about how you go to a lake or pond, they silt in from the upper end. Okay, because that's allochthonous silt is coming in, it hits the lake water, change in velocity causes a drop, and they tend to silt in from the upper end. Okay. And often these many anthropogenic causes. Everybody know the term anthropogenic? What does it mean? Yes, anthro means human, genic means source, human source problems, human activities, often anthropogenic. So for example, agriculture, farming too close to the stream banks tends to cause a lot of erosion that then easily can wash into the streams. Livestock coming in and out of streams basically are causing all sorts of problems, bringing sediment in with them and eroding banks. Development, okay, so when people start clearing land to put up a new Hardee's or Chick-fil-A or something like that, basically you have, because of those operations, you get overland flow carrying in sediment that way. Okay, so what does all this lead to? It leads to what are the impacts? Why is sediment bad, or is it bad, or is it a wonderful thing? What are the impacts of sediment on aquatic systems? First of all, deposited sediment. I tend to think, when I'm talking about sediment, my fisheries hat is on right now, just to warn you. And I'm thinking a lot more about fisheries than anything else. Okay. One thing is, there are all sorts of critters live at the bottom, they become buried. Okay. So you tend to lose benthic organisms. So food base, be it clams, insects, macroinvertebrates, whatever, are going to be, they're basically could be lost. Okay. Fish have a tendency to, a lot of fish need somewhat large particle size, sometimes gravel, sometimes sand, but sometimes gravel, cobble, or pebble, and these for their spawning areas. If you have this constant siltation rain filling these in, then basically spawning areas are lost because too fine in sediment. The other thing is the whole bottom becomes the same. Again, I've already made this point. We've been beating it through your head, the importance of habitat heterogeneity. That's why we build fish attractors. That's why you you work on shoreline development, all these sort of things. The reason is because you need habitat heterogeneity. And the other thing too, I mentioned this in the pond management lecture, so I switched these two lectures back and forth. Okay. As the bottom silts in, you're rising, what used to be limnetic zone is slowly becoming littoral zone. So you're bringing the bottom up to the photic zone, and once that happens, that's gonna facilitate aquatic plants growing, and once aquatic plants start growing, the rate of death of your pond shoots way up. So ponds quickly fill in. That's why there's such a horrible problem. So what about suspended sediment? So that was all just deposited sediment problems. Suspended sediment, first of all, it's shady. If you don't have as much effective light penetration, that's going to affect algal production. If that's the major food source of your community, then you've affected the entire food web. This is a big one. Again, this is fish directly. Many game fish are sight predators. So if you can't, and especially bass, if you can't feed by sight, then you've got a real problem. Gill clogging. Again, the surfaces they start to clog up. You get buildup of slime, and those can kill the fish, both fish and invertebrates. And then, what about both of them together? Okay. A lot of times, pollutants attach to sediment, so they could actually be, because sediment, especially clays, have such small particle sizes, they tend to be charged. They tend to have, what you tend to find is that they become polar. The outside of these things becomes negative. And so they can attract positive ions. And so many positive ions, like the metals, are toxic. So you're turning these particles into these really toxic things, messing around. Also, if you think about them, they're a surface area upon which other things can live, like bacteria. So the more silt you have in the water, you have more places you have for bacteria to live. Well, bacteria is a living thing, and we know that most living things love oxygen. And so you've increased the biological oxygen demand, the BOD of these systems here, because you got all these bacteria are sucking the oxygen out of the system. If they're using up all the oxygen, well, then it's not going to be there for other things. Again, fisheries come to hand. So sediment serves as a substrate for the microbes, and the microbial demand on oxygen can turn these systems hypoxic, which means very low oxygen. Anoxic means no oxygen whatsoever, and this can kill other forms of aquatic life. All right, so how do you deal with sedimentation? Okay, so without a doubt, the best way of dealing with it is what is called source reduction. Keep it from entering the systems, is what source reduction means. Okay. Autochthonous source reduction. Okay. Stabilizing banks is a big one. Oftentimes, it's used, so we use the vegetation. Again, I've covered a lot of this when I talked about the pond studies. Stabilizing the bank with monocots to hold it together. Riprap in areas where you have high bank problems. Secondly, another thing is the sediment is happening is it tends to be rather flocculent, means it's kind of floating up in the water column. So you can draw down these lakes and then use the sediment compaction method, like the sheathless roller I described before. Use that to compact these sediments. So just the process of drying out these sediments, it's almost like you take this messy bottom, it's almost like making brick. You dry it out long enough, those sediment particles kind of hook themselves together, so when you wet them, they don't resuspend. And compaction helps with that. Autochthonous sources then, the other way, stopping soil erosion from the watershed. Again, same sort of thing. Stopping it, stop the sediment before it enters, and I did a lot of explanation of the concept of silt ponds, which basically the water comes in moving fast. It's then slowed there. That causes the sedimentation to take place in the silt pond, which is a controlled environment, and then the water is basically decanted off of that and moves on into the next system where it's low and silt. Okay, so I covered that all before. Talk a little bit about suspended sediment in general. Okay. So talk about suspended sediment in loading systems. That's what you're seeing here. This is actually a place where two rivers come together. This is the Mississippi River and the Black River coming together. And you can see the mixture of the two different kinds of water. One of it had a heavier silt load than the other. So where is sediment moved? Okay, so, and I believe both Dr. Greenwood and I have used the term water column. It's just basically everything from the bottom to the top of the surface of the water. We call that the water column. And sediment does not move uniformly in the water column. So a lot of the sediment, what is tends to then be uniform throughout the water column is dissolved sediment, also known as ionic sediment. Okay. And then you can also, besides having those, you can then have suspended particles. So this is primarily going to be clays, silts. Depending on water flow, sometimes it's the sand, not usually. Okay. What you find is at the bottom, though, the water is moving across the bottom, and big things tend to move at the bottom. What we find is basically that if you have a good current on the bottom, rocks, this material isn't washed all the way up into the water column because it's too heavy, but it isn't sitting at the bottom either. It's bouncing across the bottom. And this is called the bed load. Okay. And so these particles, they undergo this sort of movement is called saltation. Saltation means to jump. And so you have sands for sure, gravels. Sometimes pebbles will be doing this. You have to get into some pretty high grade systems for cobble to start undergoing saltation. Okay. Instead, what they're doing is what is called traction. So saltation is bouncing. Traction is just rolling across the bottom. So you can, again, streams do move these materials, but it has to be when held a storm to be actually to move bed load in saltation, some of these heavier particles. So here's a good illustration of this. So this is basically sediment transport up here. So you're seeing, so this is the dissolved and suspended material moving up here. Down here, this is bed load. You can see things are jumping. And they're showing saltation here, jumping. And then right across the bottom is traction. So the things are moving straight across. So that's basically how sediment moves in loading systems. Other thing is that I pointed this out when we were in Cane Creek, so it's a good time to point it out again. It's basically velocity change, where you're at in the stream, velocity is going to change differently. So this, if you look at lateral velocity, depends on location, first of all, in the water column. So this is a cross section of a stream right here, that we're looking at here. What you find is there's away from the shore and away from the bottom, right about here, away from the surface too, not right at the surface. This is an area of fast flow. So the water is the fastest here. The closer you get, there's actually friction between water and the air, which slows down water right at the surface. So, and then of course as you get closer to the bottom, friction against the bottom or the sides slows down water too. So the fastest flow tends to be in the middle. So if you want to average, so generally what happens if somebody wants to know the velocity of a stream, they'll take it at 20% of depth and 80% of depth and take an average. Because that gets your fast water and slow water put together. So basically that's moving down here at this area. So this basically what's turning there. So again, we're looking at this part of the stream right here. Here, if you remember correctly, I referred to this area as a cut bank when we were in the stream, and this as a point bar. And what's happening is you've got this variation in velocity. Velocity is going to be faster on the outside bend. So this tends to be extremely erosive on the outside, and it slows, and the inside bend it slows down, and so you get depositional areas here. This is really important to remember because if you're ever out in canoes and you're racing with someone, and it happens all the time. I used to do it all the time on the Wolf River with students when I was taught at Memphis. They would try to jump ahead, and so you're coming around this bend here, and so I would swing wide, and they think, oh, they're going to go ahead. They take the shortcut, and they would basically ground at the bottom. Well, of course, you get flung out. So there's a big difference. It's real shallow here. You can't see the bottom, so until basically the canoe runs into it. So one many bets that way. So again, so I'm ahead of myself. Location of the water column, also this is geomorphology we're talking about now here. Okay. And again, impacts of sediment transport, more materials pass a given point at higher velocity. So again, that just makes sense. This amount you're carrying per liter is going to be higher where you have higher faster flow. So, how do you sample sediment? Again, here it is different in all these different locations of the stream. How do we come up with a number? Okay. So, the most easiest way is what is referred to as a grab sample. And it's simply that. You grab a bit of water. Okay. Usually, it's not you want to be below the water surface because you don't want the material, again, that material at the water surface is moving slow, plus you've got surface films. And you don't want those surface films to represent the entire body of water. So basically, when I take a grab sample, usually it's down to my elbow. Basically, I consider it a grab sample. It's very easy to do. Take the sample, rinse your bottle out 3 times, and then finally take your sample. Okay. But it's not very representative. Okay. So if I took a grab sample at that depth, I'd be getting it right here. So that only gives me a little bit of the fastest flow. It doesn't tell me anything else. Over here, it could be anything. So a grab sample is not very representative. So it's great in little tiny streams, but not for bigger systems. So what I kind of alluded to before is what more accurate is what is called a point sample, where you take water at discrete depths. Okay. So if a stream is less than 5 meters deep, 5/10 of a meter, less than 500 millimeters, less than 50 centimeters, okay, stream of that, you can get by with taking one sample, and you can take that at 6% of total depth. So we put it right about there. So you see you're pretty much on the edge of that fast and slow water. You're getting both. So streams that small, you take your discrete sample. It's deeper than a grab sample, but it's not all the way to the bottom. If streams are up to 1 meter in depth, this is what I talked about before. You take a sample at 2%, 20% of total depth, and at 80% of total depth. Okay. They combine those, and they give you a better average. That works up to 1 meter. Okay. Streams deeper than 1 meter, you do all 3. 20%, 60%, and 80% of total depth. You take your samples. In large rivers, sometimes you take depths even more. Okay. Another thing you can take is what is called an integrated sample. So a point sample means you put your sampler down there to a certain depth, you opened it, took your water sample, went up. Integrated samplers are kind of cool, because what they do is you put your sampler down, you run it down at a uniform rate, it touches the bottom and comes back up. Okay. So basically what's happening is if you do that, anywhere where it's moving through slow water, it's only going to get a little piece of a sample. Where you go through fast water, it's going to get a bigger sample. So it integrates just by putting that bottle down. I'll show you a picture of the bottle in a minute. Putting that down properly, you can get a sample that represents the entire water column. So it's really cool if you can pull it off. Okay? Because it accounts for changes in velocity pretty well. So this is basically what the sampler looks like here. So here's your collecting bottle. Flow is coming this way. So water, as I'm pushing this thing down under water here, hanging from rope, I'll show you what they actually look like. This is kind of a schematic right here. So flow is coming this way. So it's flowing up in here, and as it does that, the waste gas, the air, it comes out this way. Okay? So it bubbles out. If it's coming in fast, I'm going to take a bigger sample and all that. So the trick is to get it all the way to the bottom and up to the top. So there's the intake nozzle. That's the air vent. And that's the collecting bottle there. Okay. What the actual sample looks like, it's kind of cool. This is one here. This is called this is D48 for DH-48 sampler. It gets 48, gets its name, it was built in 1948, was the first one that was there. Okay. So what you're looking at here, there's the water intake here. There's the air vent here off the side, and this is the bottle here. And it's on a rope, so if you're on a pole, so if you're in a small stream, you put this all the way down to the bottom. You have to always move at the same speed, all the way down and all the way up. Okay, so this one is used in wadable streams. So I can go all the way across the stream, take my samples, so I can account for any sort of geomorphological differences, get a bottle at each one of my points, and I've got my sample. Okay. So here it is. So again, here's the air vent here. There's the hose. The pipe goes, a pipe bottle fits in here, and of course this holds it into place. And this is called a wading rod. This rod that comes down, you can put it down on here. It's because the rod you use when you're wading in the streams. Okay. So the wading rod attachment, removable bottles are kind of important. And this is a guy actually using one of these samples. So he's walking, he'll take a sample there. What you don't see, you should have a rack of bottles with him. We could be replacing each time that he fills one of these bottles, he would replace it. It works all well and good, except problem number one. It must move at a constant speed. So basically you spend a lot of time practicing. Move that thing down and up. Spent much of my life doing that. Okay. The other problem is you want the biggest sample you possibly can, but if that bottle fills to capacity, what's going to happen is you're not intaking water anymore. There's no air outflow, and you're missing the sample, so you have to restart all over again. So that bottle has to be redone. What about large rivers? And this is where I made most of my money in my life, is doing this sort of sampling in large rivers. This is the Mississippi. This would be north of St. Louis. So probably this is a place called Keokuk, Iowa. They're non-wadable, so there's no way I'm going to walk across the stream carrying this little sampler the whole way across to do that sort of stuff. Okay. So instead, this is what the apparatus looks like. It's called a P72. It looks like a torpedo. Okay. P is for point samplers, because you can put this thing, you can put it down to a depth where you want it to be, a certain point, hit a button, sends an electrical charge down here, it opens up this valve, and will take a water sample and then close. Okay. So the bottle sits inside of here. I would grab this loop, pull it open, and the bottle sits right in there. Okay. It can also be turned into an integrated sampler. You just leave it open, and then you run it all the way down and all the way back at the same speed, but on a crank. Okay. So again, so the nozzle can be opened or closed. Okay. And so it can either do a point sampling, which is nice, and points, but if you want, you can try it integrating, but you got to move fast, because that's going to be a deep water sample. Okay. And they come in various weights. Okay. So I would work with one. This is a 50-pounder here, and I once got thrown up against the wall by a 200-pounder that broke loose. So that was, they can be, they're huge. Remember, they got to be as heavy as possible, so that because if you put down something that's not heavy, it's going to fly out with the current and change everything. It has to be able to drop vertically as best as possible. Okay. And they're operated primarily, one thing is basically there's a crane, you go across a bridge, and you can, cranes on bridges are really easy, because you can have, it's all electrical and you can do that. On boats, it's hand cranked. And it's pretty hard here. So this is a researcher putting down this P72 in the Mississippi River. That was a long, long time ago, when my beard was red. Okay. Yeah. So that's basically those would be taking water samples. When there were different ways of measuring suspended sediment. How am I doing that? Oh, great. Okay. One is so basically we want to find out how much sediment is in a unit of water. So basically, measurements of suspended sediment are measurements of concentration. And so the primary unit would be something like milligrams per liter. So if I got a liter of water, I want to weigh how much sediment is in it. One way is called the evaporation method. This is mindlessly simple. This method here, okay? What the equipment, what you need a balance. You need to be able to weigh things to know what weight is, okay? You need a drying oven. An oven that you can put at 100 degrees Celsius or a little less than that. You don't want boiling to take place, okay? And then you have a bunch of sample jars that you clean and dry. Once you've got them completely clean, you weigh them. You have an initial weight on them, and so you know exactly how much water they carry, and you know exactly how much they weigh. So I used to have a set of milk jugs, these little tiny milk bottles, and on each one I had etched its weight inside and its volume. The volumes were all the same; they all tend to be 200 milliliters, but I had to know the mass of each bottle. Okay, so procedure is very simple. You take your sample, basically these tend to be grab samples. You fill the entire bottle to the full. So you go down, grab your grab sample, slap the cap on it, so there's no air or anything else. So you have the volume of water that the volume you have in there is the volume that's written on the side of your bottle. Okay. You then take a sample, you leave it in a drying oven. Sometimes several days, sometimes up to a week, depending on how big the sample is. But basically, you just put it in there and forget about it. Okay. You come back later, and the water's evaporated off. So all you have left is the bottle and any sediment that was in it. Okay. So 60 to 80 degrees, 1 to 2 days. Yeah, that's about right. I'll do that. Okay. Then you cool the jar down to room temperature, and you weigh it again. So when you weigh that jar now, you're getting the weight of the jar, the weight of the sediment in it. And so you can simply do the math. So the dried weight of the jar now versus that initial jar weight tells us how much mass was in the sample. Tells us how many milligrams per sample. Okay. And then you would then convert that to, if your sample happened to be a liter, that your life is great because you don't have to. But if your sample is 200 milliliters, you're going to have to multiply it up by 5 to figure out what you're at. So this is a very simple process. I take a known volume of water and I weigh how much sediment is in it. Many drawbacks. Okay. Minor drawback, okay? So, first of all this gives you is total sediment. It gives you total suspended sediment. I don't know how much of this is organic or how much is inorganic. Okay, so that's all you get. That may be fine. It's a minor drawback. Major drawback, oftentimes, you think about it, that change will be so small, especially if you have a relatively small. See, the bigger the water sample is, the more you lose your precision, but the smaller the sample, the more you lose your accuracy. So, if you did a pretty clean pond and took a water sample from a clean pond, there may not be enough sediment in there to change the balance. So it's kind of a bother. This is the standard method. This is the filtration method. Much more sense. You gotta walk through this with me. Okay? Because this has a number of steps, and it tells you everything. This is what is normally done. Okay. The equipment here, you need sampling jars again. You always gotta have sampling jars. Okay. You need a drying oven yet again. You need a vacuum filtration apparatus. And then an analytical balance that basically measures to 1/10 of a milligram. And then glass fiber filter. Okay. These filters, what you've done first with all these filters, you've dried them out, they're nice and clean, they're dried, never been used before, and you put them, generally we put them in a little aluminum boat with a number on the aluminum boat, and we weigh each one of those filters. So we know its exact weight to 1/10 of a milligram. And so those are all pre-numbered, set up in boxes, so you're ready to go. Procedure, First of all, you collect your water sample. In this case, you do not fill the bottle all the way. You want to leave a headspace. Okay. The reason for that is when you bring that sample, once you take that sample, it's that bottle, you change the velocity and the material is going to start falling again. Okay. And once that material falls, you've changed concentration. So you have to be able to shake that bottle to resuspend the materials. So this is actually, so I did this all the way down, this is everywhere from Cape Girardeau all the way down to Baton Rouge. And at night in the hotel room, we would basically take our water samples and filter them out. We don't have a drying oven. We don't have the balance with it. All we have is water samples and our filters. So we would knock these out. There's a couple of guys I work with. Okay. In the hotel room, what we do is we would shake the sample so it's resuspended, put a known volume of water into this sampler, usually it's about 500 milliliters, and then pull it down on that glass funnel. Okay. Then once we have so this is taking off one of the filters here. We would take it off and we would store it in little tubes. So we now have the filter. We do this is how much sediment I got from 500 milliliters of water. Or if it was happened to be a clear day, I would probably do a whole liter. Okay. So we get back to the lab. We now dry that filter out. Get rid of all the water in it. Dry it for 24 hours. Cool it down, and we would weigh it. Okay. At that point, we know how much the filter weighed, how much the sediment weighed. Subtracted the original weight of the filter, and now I know the weight of the sediment. So at this point, I've caught up with the evaporation method. Okay. I know basically my total suspended solids. I could calculate that per milligrams per liter. So just take that, dry it out, and weigh it. Didn't bind anything yet. Okay. So the disadvantage of this is a whole lot more involved than that drying method was. Okay. But such is life, get over it. You have to do this. Okay. The advantage is much higher accuracy. Okay. That you're using much better balances. You're not trying to take the weight of a big jar and figure out how much a little bit of the sediment is. You're taking the weight of a glass fiber filter, which isn't very much, and so it's easy to find that difference in weight. Okay. Again, you can get a very small water sample. If you have 500 milliliters, it's a pretty small water sample. But the big advantage is you're not done. Okay. You've got this glass fiber filter that's got material on it. Some of it's organic, some of it's inorganic. You can figure out the difference now. Okay. So what's on the filter right now, what you've got now, it's going to be both organic matter and inorganic matter, and the sediment. Okay. So you take that filter, it's a glass fiber filter. Okay. So right now, you've got these together, so you have what is called dry mass. Okay. The next step is, okay, I can do that. Why do we go back to this? Okay. The next step, this is called a muffle furnace. Okay. You take that glass fiber filter and you put it in a muffle furnace. Muffle furnace burns at up to 550 degrees C, and you do it for 24 hours. This temperature is high enough to destroy all organic matter. Okay, so everything's gone. You've taken any carbon in there, turned it into carbon dioxide, and it's gone. The only thing that's left is inorganic matter that wouldn't burn. We call that the ash. Okay, so that's what's left. Okay, so the organic fraction is lost. Now when I reweigh the filter weight hasn't changed, but the organic matter's gone. So I just got the ash. So, just to make this simple here, so basically, what I've got here is the mass of the filter and the ash that's left over. Okay. If I subtract what the filter weighed, I now have the ash mass. I know how much inorganic component there was in that sample. So there's my sediment number. And I can flip it. What if I'm interested in the amount of organic matter? Okay. I can take my original dry amount, subtract the ash amount. We now call this ash-free dry mass. This is how ash-free dry mass is a measure of organic matter in these samples. So it's all done by math in a furnace. So that gives the organic component. Okay. I'm going to stop there, and we won't have much to do on Wednesday. Just a little bit of piece. We'll talk about indirect measures